sample. So the main objective, we need a large amplitude for which you need a sufficient pressure inside the channel. And second is a fast response for which you need an efficient electrode. We fabricate an electrode, a flexible electrode using microfibers of steel, which is very good heating element, and that enable the system to be active very quickly. Here is the actuation of our actuator. It can produce a large bending motion. And here the working fluid is ethanol, and it can be operated just using 20 volts. That makes the system quite portable. And using this motion, you can make a variety of soft robotic application. One of the applications we show here is a soft gripper that you can see here. Using 3 bending actuator, we produce a soft gripper that can pick and place some delicate objects such as bun or other food items. It's really fast, and it is directly operated by electricity without any compressed air. Now, the second project we worked on is a tunable membrane stiffness in a stretchable fiber for a programmable shape change in soft robots. So for this, we took another inspiration from nature. As you can see in a worm, it produced a bit complex motion. There are many examples in nature that produce a quite complex motion using a single chamber soft body. Here the worm have a hollow structure inside. It increases the pressure and control the stiffness of the body to produce dynamic shape change. So here there are 2 sets of fiber. One is circular fiber and another is longitudinal fiber. Longitudinal fiber is responsible for controlling the stiffness. By creating the stiffness asymmetry around the body, this worm can change the shape. So inspired by the role of this fiber, muscle fiber, we developed some hybrid fiber, a stretchable fiber that can tune its membrane stiffness to control the shape of a soft body. First, we did some abacus simulation to check how much stiffness change we require. So we found around 30 times membrane stiffness change is good enough to make shape change in a soft body. So we propose, but getting a 30 times or more than that is not that very easy in a stretchable rubber. So we introduced this concept of hybrid fiber. So this fiber have a 2 part. One is stiff part and the other is stiffness tunable part. This stiffness tunable part is a soft rubber inside which you have a locking mechanism that you can see here. The 2 stiff parts are connected using a gallium locking system. When the gallium changes phase from solid to liquid, this will be unlocked and it will be stretchable. In that way, this hybrid fiber can behave either as inextensible or as a stretchable rubber, depending on whether you locked or unlocked the fiber. Now, once we have this stiffness tunable fiber, we integrate it on a single chamber soft body, the 2 skins on top and bottom skins. And whenever the fiber changes stiffness, you will get a stiffness asymmetry around this body, and that is sufficient for bending motion. Here we show bending of a single chamber soft body integrated with our hybrid fiber. So here, first on the left skin, we change the stiffness, and as you can see, it can bend to the left. And then we revert this back to its initial position. Then we allow the gallium to cool to recover its stiffness. So the cooling takes some time, like 1 to 2 minutes. So I'm skipping that part. And later we change the stiffness on the right side. And then the actuators can bend towards the right side as well. So in that way, this single chamber can behave as a simple manipulator. Here we show another complex shape evolution, which can kind of mimic the motion of elephant trunk. We have a set of fibers inside it, and the fibers change the stiffness at different locations, and that's how it produces a complex shape. And this is the current work, the current thing I'm thinking. So in the last 2, it's bidirectional bending movement. Here we trying to make a bit more multi motions to have a more degree of freedom for the actuator. So here we have 4 fibers and have some special design inside. And by changing the stiffness of this fiber, you can get a shape change in a different direction. Of course, there is a cooling time involved, which I cut here, as you already have seen this, just because of the time limit. So that's the end of the presentation. If you have any question, of course, I would be happy to answer. Thank you.
Thank you, Ragesh. I actually have a question myself. your whole presentation goes around the topic of soft robots.
Yeah.
But why would you use a soft robot? You could obtain the same gripper-like system you showed by using a hard robot, couldn't you?
Yeah, imagine like in a hard rubber, when you apply the force on some delicate subject, for example, take an egg. If the force is, if you increase a little bit higher, it's going to damage your object. But with the soft robots, it will be much more safe for interaction. It's not only with the egg or delicate object, but commonly, if you're using a robot in your home or offices, I mean, this hard robot, even a small error could give a potential, it could be harmful for human being and surroundings. So in that sense, soft robot is much more safe for interaction. Apart from that, these are rubber and cheap material. In future, you will be able to 3D print most of the part in a single stretch. Probably you will be able to integrate the electronic and every part together in a single printing. So in that sense, people think that it will simplify the existing technologies.
Yeah. Thank you. I see that there is a question as well from Gerard Fernando.
Yeah, okay.
Is there? So go ahead.
A couple of very quick questions. With your first example, what is the response time during cooling? And the second part to that question is, when you're heating out, what is the evaporation rate for the ethanol after 10 or 15 cycles?
Yeah, we did a cyclic tensile test at least for 30 cycles, and it still worked very fine. I mean, this is the one part we want to work on to develop some soft cooling system in the next stage. Now, for the cooling time, how much it takes? Usually 20 to 30 seconds it takes to come back, but still it's faster. It depends on how quickly you inject, and we actually provided a very thin membrane for this actuator that also helped to improve the heat transfer to the surroundings in terms of conduction, convection, and radiation. So this is something we really want to work on future to improve the cooling speed as well. Yeah.
Fascinating work. Thank you.
Yeah, thank you very much.